Double tap another one. I'm pretty sure I already did this one, but we'll double tap it.
You may have heard about a recent and very exciting measurement announced by researchers at Fermilab.
The
accurate measurement of the mass of the W boson.
Reading my diary.
This measurement was both made with unprecedented precision and, even more interesting, it disagrees with modern theory. If this measurement is confirmed, it could be a solid hint that we need to revamp our understanding of the laws of nature. The prospect of breaking our theories is an exhilarating one, and I want to tell you all about it.
We're going to get into it. I've watched this before, actually. Wait and drop in 2.1 mega electron volts here in a minute. I'll show you what it looks like.
The W boson is one of the particles that transmit the weak nuclear force. It comes in two versions with an electric charge of +1
but right
and
now
the other
lambda.
-1.
Well, actually,
we don't distinguish between the two variants, so we just say
negative
W boson.
I'm unprimed.
The other particle that transmits the weak force is called the Z boson. It is electrically neutral, which means there's only one version of it. The W and Z bosons were postulated in the 1960s, and they were discovered at the CERN laboratory in 1983. Our modern theory, which we call the Standard Model, makes no predictions for the mass of either of these particles, or, for that matter, any of the subatomic particles. But it does make predictions about how they are related.
Well,
for example, if you know the mass of a couple subatomic particles, you can predict the mass of others.
Think about it like
I'll have more to say about that
nitric
later.
acid and
an accelerator called LEP
next to each other,
operated at the CERN laboratory from 1989 to
water
2000.
with a piece of gold.
It produced some 18 million Z bosons distributed between four distinct
the
experiments.
alpha or beta, something,
These experiments measure the properties of the Z boson to exquisite
oxidizing
precision.
it the way I need
It'll
it
be
to.
a long time before
You're
the
going
LEP
to need to know the
measurements
electron shell.
Indeed, they may never be surpassed.
It is.
The mass of the Z boson was determined to be 91,187.6 plus or minus 2.1 million electron volts.
Later when we talk about Lenz's law,
don't worry too much about the meaning of these units because I'll use the same units throughout. The important thing is the uncertainty, which
you're
is
traveling down the pipes
MeV.
right now. I mean, you're just...
The recent announcement by Fermilab is a measurement of the mass of the W boson with an uncertainty of 9
overhead
MeV.
of the weights. You're pulling in,
now that's
going
much
in,
worse than has been
north
achieved for the Z
my
boson.
compass. See,
But
I
before
actually
this
would
recent
know.
measurement,
Well,
the
you
best
walk into the
uncertainty
building no matter
anyone
what you
could
would
achieve
do,
for the W
follow down
boson
and
was
do that,
about
but
20
orientation
MeV.
matters.
So this is
what
a
is
huge improvement.
2.1?
It's
Let's
part
get
of
this
a
out of
multi-year
here. I
effort
don't
to
want to
measure
waste
the
time
mass of
saying
the W
numbers.
boson
2.1.
as precisely as we have
And
the Z
if there
boson.
was 10 people,
Okay, so let's talk
and
about
2.1
measuring the
was
mass
my
of the
regular
W
Z
boson.
boson. It's
The
my
LEP
weight,
accelerator
which is
wasn't a
normally
great
1 or
place for
0,
making W
100%.
bosons, so their
Or
measurements
all
were
me
all
or
in
none of
the
me.
50 or 60
And when they go
MeV
tracking
range.
people and mill like white hats,
But the Fermilab
Fed or
Tevatron
safety
was a great
officers,
place to
you
make
got to
W
pull that
bosons.
down to like they
Tevatron
understand
operated
safety
from
at
the late 1980s
2.1
through
mega electron volts of
2011,
this thing
and
passing
millions
through,
of
and
W
how dead you'll
bosons were
be,
generated.
how far you'll walk down
There
the
were two
road,
detectors located
curious,
in the Tevatron called
pass through your
CDF
body.
and D0. The recent announcement was made
Now,
by researchers
go
using the
figure
CDF
that's not
detector.
really necessary
And just
out
so
here
you
in the
know,
mill.
I've been a member of the D0 experiment since 1994. So how do you go about measuring the mass of the W boson? Well, the first thing to note is that you don't put a W boson on a scale and weigh it.
But
For one thing, they don't live very long.
Well,
They decay in about
cesium,
3 times 10 to the
right?
minus
That cat's
25
just not going
seconds.
to make it anyways.
Even traveling
right?
at the
Super
speed
stable.
of light, they travel about a tenth of the diameter of a
Now,
proton
let's say that
before they
marshmallow
decay.
was
That's long before they hit
any
a detector.
marshmallow.
So how do you study them?
Here's a person.
Well, what you
him,
do is look at
me,
the particles
this
into which
picture.
they decay and measure those particles' energy and momentum.
How do they take
You
it?
then use the laws of energy and momentum conservation and work backward. This is how the mass of all short-lived
So
subatomic
this is me
particles are
hacking
measured.
FX right
This
now.
particular
we're in this. Then
image
we're
is
doing
from
this.
CDF,
Then you're
and it
going to
contains
crack
two
your local
W
clock and
bosons
come
from
back in
top
here.
quark decay. W bosons can decay into two distinct paths. They can decay into a quark, an
you walk
antimatter
into
quark, or they can decay into a
boot camp,
lepton,
right?
like an
What's
electron or a
quarky?
muon, and a
Now,
neutrino.
you've been here at boot camp.
On the
You
one
walked
hand,
in here with a
you can
leadership
detect
formation,
quarks
even
pretty
though
easily
it
in
is
your
right.
detector. But it's hard to
We want to
precisely
stay
measure their
inside
energy and
leptons, what
momentum,
we like.
so this type
Neutrinos
of decay
pass through
isn't
everything.
used
They
for
keep
precise
they keep
measurements.
walking, but
On the other hand, modern experiments can measure the energy and momentum of electrons and muons very well, so that's attractive. However, on the third hand, neutrinos pass through the detector without interacting, so you have no direct information about the neutrino. That's a problem, but you can estimate the energy and momentum of the neutrino by measuring everything else. Since the momentum is conserved and the total momentum before the collision is zero, the momentum of the neutrino should be the opposite of everything else.
Anyways.
You can then use the measurements